Welcome, everybody. This is the third edition or the third episode of the TwInsider short webinars, which is putting the spotlight on our 8 demos. And today we have here the representatives of our Slovenian demo. Alexander Mumirovski from the Electro Institute Milan Vidmar and Urbardes from University of Ljubljana. So there are two different use cases will be presented in two parts. And yeah, I would suggest not to waste more time, but giving the words straight to you, Urban. So you can share your screen and then go ahead with the presentation.
Okay, so thank you very much for the introduction. So I would like to thank everyone for logging in and to expressing their interest in the Slovenian pilot, which we developed during this TwinEU project. So today's presentation will be split by myself, so Urban Rudesh from University of Ljubljana in Slovenia, and my colleague Alexander Momirovski from Milan Vidmar Electric Power Research Institute. And first, I would like to say a few words about the team. So we have five institutions collaborating on the Slovenian pilot. The first one and the pilot leader is ELES, who is a combined transmission and distribution system operator of Slovenia. Then there's the University of Ljubljana, Faculty of Electrical Engineering, which is actually the oldest and the largest higher education and scientific research institution in Slovenia. Then, of course, we have Electro Institute Milan Vidmar. Elektro Gorenjska is one of the Slovenian distribution companies, and HSE, which is a national producer and seller of electricity in Slovenia. So we have 5 partners. And the main motivation behind the Slovenian pilot was that we're currently in the process of a dramatic increase of converter interface generation in Slovenia. And this goes both for the distribution and the transmission network. So the main objective was to tackle the issues which arise from this and to upgrade the stability management process which goes on or which is under operation in Slovenia. So here we basically tackle 2 different aspects. The first one, we plan to increase the system observability, and the second one, improve the controllability of the system. So this is why the 2 main contributions of the Slovenian pilot can also be split into 2 ways. So the first one is to develop the real-time static and dynamic security assessment tool, addressing the observability problem. And the second one, develop the fast frequency response service, which tackles the controllability problem. So first, a few words about the digital twin for power system stability. So we can all understand the terminology digital twin in different ways. So it's this term digital twin is more or less application dependent, but whenever we're talking about the power system stability, we cannot avoid having, let's say, exact and appropriate power system models. So basically, in the context of the stability, the expectations that one has towards the digital twin are the following. So the first one, the digital twin needs to capture both static and dynamic system states. The second one, it needs to execute simulations and security assessments. The third needs to provide clear stability margins and indicators related to stability. And the most important one is the fourth one, which means that it needs to do all that fast enough for operational decision support. And you will see in my last slide that we managed to get all the results within a couple of minutes, which we think it's a very, very good result. So whenever we were discussing the stability-oriented digital twin, we were discussing about the dynamic security assessment tool, or the so-called DSA tool. So this DSA tool basically has its core, and this core is basically constructed by static and dynamic models of the power system. So before we go into the models, I need to present how the whole DSA process was, let's say, planned, or how it was constructed. As I said, the core of the DSA are the models. So Slovenia is quite a small country within Slovenia. So this means that this orange part, this SI model, this is a, let's say, model within the Slovenian national boundaries. It's detailed. We have a lot of information about it, but it's not enough to help us understand how the dynamic response of our network will look like whenever there are some serious faults. So this is why we needed to extend this model beyond our national borders and to include the observability area as well. And apart from that, also include the equivalents representing the remaining of the continental ENSOI interconnection. So we have our model, which will be very, let's say, the most important part of the DSA constructs from three different parts, right? So the national model, the observability area, and the equivalent of the ENSOI. Now, those three elements are then automatically merged together and initialized from the SCADA inputs. So this means that the whole DSA process is being initiated by the data, highly relevant data from the SCADA, which runs in the LS control center. And then we are using this model to train AI, so artificial intelligence, in order to help us to speed up the whole process. But the first thing is that whenever we initialize the whole model, we run the power flow calculations. So this means that these are the static calculations. And we, of course, compare those calculations with the state estimator results from the SCADA. And whenever we detect the sufficient match between both, and this is the case in 99% of all situations, this is when we go into the time domain calculations being run by the DSA. Now, this process is usually very time consuming, and this is why we're using the AI model providing, let's say, some initial estimates of the stability indices, the stability margins, in order to skip quite a lot of simulations, and in this way, speed up the whole process. And whenever the results are completed, those stability indices are visualized to the users. So this means that to the system operator for the purposes of more appropriate, let's say, more informative decision-making during the control. So let's dig in first into the distribution grid. So the idea is that static models, the PQ models of the distribution grid are no longer appropriate for the conditions where we have a lot of distributed generation, where we have a lot of battery storage system in the distribution grid. So this means that we were studying different ways how to aggregate all those devices in the distribution network, keeping that aggregated model as simple as possible, but at the same time, enabling this model to show the most, let's say, the most appropriate dynamic characteristics of the distribution system. So in the next phase, we launched two measurement campaigns where we got a lot of information from how the actual distribution network reacts to different situations. And this was basically the most important input for parameterization of our load models. Then, based on this, we were able to construct active and reactive power dependency on the voltage. This is the point number 3. So those first three steps were basically systematic approach to modeling the distribution network. And in the on the fourth point here, we're showing how different types of loads react to different kinds of voltage set points, so on-load tap changer set points. And you can see that different types of loads, different types of distribution systems also react differently, dynamically differently to this let's say, events. So the idea is of modeling the distribution grid was to replace the conventional PQ static representation of the distribution grid into something which is much more appropriate for the modern distribution grid with all those complex devices connected to it. And this was basically one of the key components for our DSA. So now that we have the distribution grid, we included this into the national transmission grid model and built the whole, let's say, observability area and the NSOA equivalent. And we did this in the fully automatized way in the Python environment and within the Power Factory toolbox. The problem here was that the parameter availability of the power systems outside the national borders is quite limited. So this is why we also launched one of the pan-European scenarios. This is a scenario number 5, in which we exchange data with our Hungary colleagues, and in this way show how important it is for our national TSO to have enough information about the dynamic properties of the neighboring grids as well. Because up until this point, until we launched this scenario, pan-European scenario, basically what we had was only the generic information about the types of power plants, the control models abroad, and so on and so on. So this pan-European scenario was something which actually brought our DSA let's say one level above what we expected. Then the next phase was initialization of our model, which I already said, this was done by the SCADA snapshots. Then we're checking compliance with the model limitations. We correct any potential model problems, and then we run the simulation test, checking whether the model is stable or not. After that, we run the static validation. So this means that we're comparing the power flow calculations with the reference state estimator values. And as you can see on the right-hand side of the slide, the average value, the average error is somewhere between 1%. So we think that when it comes to the static representation of the system, the results are very good. So everything which you can see with green is basically fully automatized in Python. The only thing which is not fully automatized is the dynamic validation of the network, and this is quite understandable because static conditions are always present in the power system, whereas dynamic events are not. So we were not able to automatize this because we will have to wait for any kind of faults, outages, and so on in order to get the dynamic response from the system and to validate the whole process. So this is why the dynamic validation was done in the manual way. And then we started our calculations. So we get our digital twin, we get our scenarios, and the first thing, which was the most important thing for us to speed up the whole process, was to parallelize the whole problem. So we're running all the scenarios in parallel. So all the stability limit scans are done in parallel, and which you can see from this slide that the scenario, which is the longest, basically defines the total simulation runtime. So these parallel calculations, which are enabled by the Power Factory tool, was the one which helped us to decrease the calculation time the most. The second thing was AI support. Here on this slide, I'm showing you how the AI guesses the actual results. And with the green bars, I'm showing you the results of the critical clearing time. This is one of the indices we were observing. So these results were obtained by the dynamic simulation. So we're considering these green columns to be the correct value, right? And the AI provided the values shown with the blue line. And you can see that for the initial guesses, those AI-supported stability scans offer very, very good indication. And in this way, we avoid doing too many time domain simulations, and in this way, we decrease the calculation time for quite significant portion, and you will see in the continuation the exact numbers. The third very important part was the user interface. So on this slide, I'm showing you how the input interface looks like. So basically, on the left-hand side here, you can input all files related from the state estimation for the initialization. You enter the whole models which you have on your disposal and so on. On the right-hand side, you select the type of stability you're interested in. If you prefer to put focus into certain, let's say, power plants, you can select them if you would like. And then you basically just start the whole DSA process. And in the output terminal, you have the information of where in this, on which phase of this process the currently DSA is in. And once the results are complete, we're plotting them in quite innovative way. And this is the representation of the results of the transit stability assessment. So the scenarios being simulated are three-phase faults, and the indices, stability indices, are critical clearing times per individual source. So on the horizontal axis, we're plotting individual sources, and on the vertical axis, we're plotting the CCT as an index. And you can see this horizontal line AI limit. This is basically the arbitrary set limit above which we do not, for the CCTs which are above this limit, we do not run any kind of time domain simulations because those are the situations which are not critical. For all the values below this, basically the AI suggestion is considered only as an initial guess, but we double check all the results with the time domain simulations. So all of the values below this limit are double checked with time domain simulations, but the number of those simulations is drastically decreased. The second type of stability is the frequency stability assessment, where the scenarios are basically the outages of large power plants in the Slovenian network and abroad. The stability indices are basically rate of change of frequency values per individual source. And this is why the most important, let's say, impacting factor to frequency stability is the inertia constant. So this is why on the left-hand side, we're plotting the current inertia value of the Slovenian power system. And we're also plotting the location of individual machines on the map. And you can see here we have some kind of a traffic light identification where we can see whether the ROCOF value is critical or not for individual machine. And if you click on individual power plants, basically you see the details about the scenario in which those ROCOF values they actually took place. Now, the third type of stability is oscillatory stability, or the small signal stability assessment, in which we basically run only one scenario and where the stability index is the relative damping of oscillatory modes. And on the left-hand side, you see the innovative representation of this, let's say, relative damping, where we have this kind of a clockwise representation, in which on the radial axis here, we're plotting the machines or the power plants, and the relative damping is basically plotted depending on the location. So we have 3%, 6%, 9%, and 12% relative damping. So the bubbles shown in this representation shows the participation of individual machines in particular oscillations. And on the last slide, before I hand over the word to my colleague Alexander, the time requirements for doing these calculations. So on the top part of the screen, I'm showing the results for, let's say, more simple case in which not many machines were operating. But on the lower part of the screen, I'm showing basically the most complex scenario in which most of the power plants were operational in our network. And you can see that without AI support, in this simple case, the time required was a little less than 3 minutes. But we're providing AI support. We basically decrease the value for 35%. But when it comes to this complex problem, which the time domain simulations are really time depending, I mean, very time consuming, you see that without the AI, we need to wait for almost 11 minutes to get the initial results. But with AI support, we decrease this number for even 60%. So we get the results below 5 minutes. So we think that those two numbers, so 1.7 minutes and 4.3 minutes, this is something which we can be very proud of. And this is something which can offer the TSOs, or LS in particular in this case, very good indication of the stability limit of each operational state the power system is under at the moment. So with this, I would like to hand over the presentation to Alexander to continue and to present the controllability part of the Slovenian pilot.
Thank you very much, Urban. I didn't had the chance to take the control, but I will share my screen. Just a second. I would like to know which, because I have a lot of monitors in front of me. So here we are. I hope you can see my.
Yeah, we do. Just extend the presentation.
Yes. I have to share another. Just a second. I will stop the sharing and put the actual monitor. Now we have the actual presentation. We'll start from this part. Can you see the presentation? Oh, we can go like this.
Yeah, that's fine.
At this point, I would like to emphasize and express special thanks to our Slovenian colleagues who put a lot of team effort in this Slovenian demo, and really, I'm really proud of them, and they're still putting a lot of effort providing the final stages of the deliverables before we send them to our external reviewers and publish them in the third or fourth quarter of this year. Now we're going to see the Slovenian demo from other perspective, which is the controllability perspective of the Slovenian demo. And that is the actual concept provision of fast frequency response. And at the very first beginning, I would like to say a few words about the guidelines we had to develop in order to further develop the FFR service within the scope of the TwinEU. So at the very first beginning, we tried to ask ourselves what are the crucial questions of this service? What is the broader picture? So no matter what the scope was, we started from the nature of this FFR. How can the model market, model of the market sustainability and compliance can be? And also, we had to choose our simulation environment, data, an area of interest, and also the techno-economic vitality or justification in the system. But all in all, we had to keep it really simple, continuous, really precise response or ancillary service in the future with short duration, and also this response to be with local influence, but with the character of the wider market in the synchronous area of continental Europe. So at the very first beginning, we had to distinguish between the FFR and synthetic inertia because we found out that the actual distinction between these two responses can be a little bit confused between them, and but they are not interchangeable. So FFR is a quick active power response to frequency deviation in our case. But the synthetic inertia is actually an instant power response to a time derivative of that frequency deviation. So with our FFR, we want to almost instantly arrest frequency deviations and to persevere the frequency nadir within its tolerable limits. So actually, FFR is the bridge or the layer which connects the inertial responses and the slower responses from the primary responses, even in frequency sensitive mode or limited frequency sensitive mode. So at first, we created the static command, which is the command which can be realized if we had an instantaneous response from the FFR. At the first look, it really looks like LFSM, but it's quite different because it's actually quicker with a reserve capacity, and actually it's not provided by some static, but with actual targeted numbers and characteristics. And at this point, I would like really to emphasize that behind every of this number, there is a story which can be actually read about in the deliverable, in the upcoming deliverable for this FFR concept. So the FFR, we activate FFR where the deviation is 200 millihertz with full activation at 800 millihertz because we wanted to have the real capabilities of the elements which could provide this kind of service. And as you know, it's trivial to emphasize the dynamic realization of this kind of service because the devices or the elements which can be the providers of this kind of response are not unlimited regarding their ramping capability. So we had to be really realistic in this field of the development. We had a lot of iterations with different kind of technology vendors or providers to get the realistic response and to be really realistic about the development, about the further development of this response or auxiliary service. Of course, at the beginning, at least from the technical part of view. So what we were dealing with, we had our sequence of a static PF command, then the dynamic realization with its own parameters, and then we had actual delivery of FFR, and we had some theoretical and also simulation part of FFR in the digital twin of the system, for which we are going to talk about in the continuation of this presentation. So we analyzed the disturbance to FFR ratio, different system inertia levels, a lot of levels of rate of change of frequency at the initiation, and we were actually doing a lot of sensitivity analysis at the very first beginning with the parameters of the FFR. So we actually targeted a lot of these parameters, but at the very first beginning, we found out that this is really dependent on the system structure, and the best we can get from the theoretical perspective of view is something that are only guidelines, and these guidelines will be a really integral part of the deliverable and the actual development of this FFR concept. We can emphasize the fact that FFR can limit the frequency deviations, but in some cases it's quite impossible to limit these frequency deviations, but at least they can limit the rate of change of frequency post the disturbance states of the system. So as we were testing different parameters, we were actually even facing the main technical challenge of the FFR, that is the FFR planning. So one of the crucial analyses we did were the relation between the total FFR capacity, the tolerable Rokov in the area for different inertia constants. And we would like to emphasize at this point that actually every element at the high voltage who is capable of providing FFR and who is capable techno-economically to reserve a dedicated FFR capacity can be compensated with closed agreement for this provision. And regarding this planning, we're really want to express the fact that maximal dispersion of these devices on the high-level grid within the control area or one country, it must be preferably coordinated with TSO's emergency and restoration plans. Now, just a few minutes to show the demonstration part of these actual FFR responses. So we started from the very first, from the same actual backbone of the system, but we diverge from them in a manner to upgrade them in a really detailed manners, because we were dealing with some system splits, some emergency states of the system. So every detail had to be modeled. We had a lot of use cases, and all of these use cases will be and are already described in the deliverable. But what we would really like to emphasize that in the interconnected connection of the system, the impact of the FFR is quite minimal. But when we're dealing with some severe system splits, then the impact of FFR is quite beneficial. The states between, or the dynamic responses between the dynamic continuation of the frequency with and without FFR is really uncomparable. So we had a lot of simulations, but we really had to emphasize only the representative use cases to be understandable what FFR does to our system and frequency stability. And we can say that in even smallest or smaller system splits or islanded operation, the FFR is the most beneficial in these states. So I would like to now go just to the conclusions, because I know that we are a bit limited with the time. So in the Slovenian demo, we had two perspectives of use. The first one is observability, when we emphasized the DSA tool, which enabled integrated transmission and distribution digital twins. The DSA deployed within ELIS, that's Slovenian TSO, virtualized infrastructure, and the DSA, which is part of the observability perspective of this demo, created a roadmap toward operational DSA integration in the real system at ELIS, offline and also online, for offline and online stability. There was also developed an AI-assisted DSA with simulation-based validation. Also, substantial AI-driven acceleration of these DSA workflows was created. And last but not least, near real-time identification of potential stability issues were actually expressed in this demo and provided, and this is one of the most crucial parts of this Slovenian demo. Regarding controllability, the concept of FFR was developed, and we can emphasize that FFR is a crucial service or ancillary service for the stability of the system, especially during system splits, smaller isolated islanded operation, and resynchronization of the system. However, there remain market and regulatory aspects which are still a challenge, but also represent an opportunity for further work and further development. And last but not least, the stakeholders were really expressed technical willingness and preparedness for this kind of service, but they raised some concerns regarding the market viability and techno-economic feasibility of this service. Thank you very much, and if you have any questions, please contact me or Urban, and we will be ready to ask your questions. Thank you very much.
Thank you very much, Alexander and Urban, for both of the presentations, and thank you for being so much focused on the results and achievements that you have been able to develop throughout this little bit less than 3 years. So indeed, time is running out a little bit, but maybe we can still open the floor for one question. So if there is a question, please just raise your hand, and I can open your mic and camera. But in the meanwhile, I can also tell you that we are going to share all the slides and the video after this session. So you can take a closer look on those slides there. Alexander didn't have that much time to go through in details. And also there is one more session, one more episode of TwInsider Shorts coming up before the summer break. In 2 weeks' time, we will take a look at the achievements and results of the German demonstrator of TwinEU. Okay, so I don't see any hands raised. So then with this, I would like to thank again for you, Urban and Alexander, for these presentations, and also for the audience for joining us. And yeah, we'll see you next time. Thank you.
Goodbye.
Bye bye.